Imagine a future where humanity must choose a new home beyond Earth. Two of the most often discussed candidates are Mars and Venus. At first glance, Mars seems the obvious choice. It's been captured in our imaginations for decades. We've sent rovers, probes, dreams toward its red horizons. Yet Venus, often dismissed as a hellscape, offers surprising advantages that might make it the better option in certain respects. Let's journey through what life might be like on each, what it would take to survive, to build, to eat, to use what's there, and in the long run, which might truly be more realistic and sustainable. First, let's meet the planets. Mars is the red planet, distant, cold, less massive than Earth, with thin atmosphere, 96% carbon dioxide, making breathing something only possible by reliance on artificial systems. Gravity on Mars is about 38% that of Earth, meaning you weigh less, walk differently.
We're making good
have to
progress.
get used to not having the familiar pull of Earth's mass beneath your feet. Temperature swings are extreme. Water exists, but mostly as ice or some bound up in the soil. Any liquid water on the surface is rare and transient. Mars is about 175 million miles roughly to 180 million kilometers from Earth, depending on where each is in its orbit. It's smaller than Earth, half as wide roughly, which poses potential issues for atmosphere retention, geological activity, and long-term habitability. Venus, on the other hand, is almost Earth's twin in terms of size. Its diameter and mass are very close to ours. It orbits closer, about 160 million miles to 160 million kilometers from Earth in its more favorable positions. Gravity is about 90% of Earth's, so living there would feel more familiar in terms of weight. But Venus has a reputation, scorching surface temperatures hot enough to melt lead, clouds of sulfuric acid, crushing pressure at its surface. Yet about 50 kilometers approximately equals 30 miles above the surface, the atmosphere is far more benign. There, the pressure and temperature can approach ranges tolerable though still extreme for human technology. Get a handle with the right engineering. Also, Venus's thick cloudy atmosphere would provide shielding from solar and cosmic radiation. Mars's thin atmosphere offers almost no protection in that regard. So with that basic heads up, let's compare in 5 major categories: dwellings, homes, food, resources, realism, which is more feasible soon, and long-term prospects.
Affirmative.
Homes
Its
and living
crystalline
spaces.
structure is unique.
On Mars, one of the biggest challenges is the atmosphere. Almost no oxygen, nearly all CO, extremely thin.
We can establish a forward base there.
With full life support.
Agreed.
Gravity being low means people would have to relearn movement, more hopping, more risk of muscle and bone loss over generations unless mitigated. Transportation of materials from Earth is extremely expensive in terms of energy, cost, time several months for a mission back for more supplies. So using in situ resources is crucial. NASA once held what they called the 3D Printed Habitat Challenge, where designs for Martian homes were submitted. One winning desert Marshall's made of basalt composite, eco-friendly, for levels including kitchen, sleeping, recreation. There are ideas for subterranean dwellings internally carved from Martian rock, or even igloo-style domes built into hillsides, for thermal insulation and protection against radiation. But realistically, living inside dark, sealed structures for your entire life sounds grueling. No fresh air, no direct contact with nature, limited sensory diversity. On Venus,
watch your step here.
You couldn't live on
Copy
the
that.
surface except maybe for very short scientific missions. It's too hot, too corrosive, too high pressure. Instead, the better idea is floating cities in the sky about 50 kilometers above the surface and the stratosphere. NASA's Havoc high-altitude Venus operational concept imagines airships, floating platforms, floating habitats,
Maintain altitude,
all engineered to resist sulfuric acid in the clouds, engineered to maintain acceptable temperature, humidity, pressure. The clouds might seem dangerous, but if systems are well sealed, with air conditioning suited to counter heat, corrosion, with UV shielding and acid-resistant materials, above the thickest cloud layer, the environment could be surprisingly manageable. Think of communities suspended in the sky, connected by aerial bridges, shifting, floating, rather than built on solid ground. Next, food. On Mars, there is proof of water, mainly ice, or bound in soil. That water could be melted or extracted and used in greenhouses to grow food. But the environment is cold, low pressure, low oxygen. Growing Earth plants will require replicating those environmental conditions. Greenhouses under domes, artificial lighting, or filtered sunlight. Soil that may need amendment because Martian soil has perchlorates and is not naturally rich in nutrients for Earth plants. Food will probably be mostly plant-based. Vegetables,
We need to move
fruits,
fast.
seeds,
Agreed.
nuts.
The anomaly is
Meat and
just
dairy
beyond
will
that
be
ridge.
rare or very expensive, probably reliant on lab-grown or imported. Non-perishables from Earth would still be essential for a long time. Also, since Mars's gravity is lower, soil might retain water longer, which is a small help. On Venus, if floating habitats are established, growing plants becomes possible above the harsher surface. But there's no definitive proof yet of free water on Venus. So water may have to be generated or shipped, or chemical processes used to split atoms and recombine, though that's energy intensive. Growing plants in greenhouse-like modules hung from floating platforms. Using artificial water systems, perhaps recycling. Also, acid rain and sulfuric acidity present extra challenges. Materials must be resistant.
Confirming
Systems
trajectory.
must be highly
Proceed with
sealed and
platform
clean.
74.
Then, raw materials and resources. Mars is rich in iron, nickel, sulfur. These could be used for building, manufacturing, bridges, beams, structural components. Iron for construction, nickel maybe for electronics or other specialized uses. Sulfur for certain chemical processes like batteries. Because of Mars's ground, there is rock and regolith, metals, minerals accessible, especially in plains, canyon walls, craters. Transporting heavy materials from Earth is expensive, so the more material you can source locally, the better. Venus that has many useful elements: iron, nickel, titanium, aluminum, silicon. Floating platforms could harvest from the atmosphere or from near surface or near cloud materials. Silicon is
Drone
especially
5,
valuable for
proceed to
solar
rendezvous
panels,
point.
which could be extremely
Maintain altitude.
effective. Given Venus's relative closeness to the Sun, aluminum, titanium, corrosion-resistant materials for airships. For the structure of floating habitats, the atmosphere also gives protection as noted in closeness to the Sun. It might allow more solar energy per unit or useful for power generation, though needing to deal with heat and corrosion. Then, realism and feasibility. Mars has been studied deeply. We have multiple successful landers, rovers, orbiters since 1970s. NASA and others regularly simulate Martian environments. People propose human missions for the 2030s. Infrastructure, plans, research are far ahead. The psychological, physiological challenges of isolation, low gravity, radiation exposure are being studied. Venus is studied too, but mostly for its atmosphere, and for probes, landing is difficult. Surface is extremely harsh. The floating city concept like Havoc is more speculative. We have not yet sent many missions intended to establish habitats high in Venus's skies. The technical, material, engineering challenges are greater in some domains. For Venus, need acid-resistant materials. Need to build floating structures that can endure severe winds, corrosive clouds. Finally, long-term possibilities. Suppose over centuries and millennia, humans manage to settle both. Suppose also terraforming or atmospheric engineering might become possible. On Mars, people might adapt genetically or physiologically to the conditions. Lower gravity, colder, less atmosphere, depending on how terraforming proceeds. Perhaps rotating habitats for warmth, thicker atmosphere replacement, greenhouse warming, injecting greenhouse gases, redirecting water, etc. Over time, Mars maybe could become more Earth-like, assuming we solve atmosphere, magnetosphere, water, etc. Venus's terraforming is more speculative, cooling the surface, reducing the thick CO atmosphere, perhaps solar shades, chemical reduction of CO, injecting oxygen, relocating or neutralizing sulfuric acid, etc. Days on Venus are long. Solar day from sunrise to sunrise on the surface lasts longer than 100 Earth days, making for strange cycles. But in high altitudes, perhaps day-night cycles more manageable. One obvious risk: being closer to the sun. Venus is more vulnerable to solar events, to the eventual fate of the sun. In about 5 to 7 billion years,
Maintain
the
orbital
sun's
precision.
evolution will make Earth unlivable.
Resource transfer
Venus,
is critical.
being closer, will be even harsher. However, Mars will not escape eventual cosmic changes. Putting it all together, the video concludes that in the short to midterm, Mars seems more realistic. We already have much more study, more missions and planning for human landing, materials, infrastructure, habitats more within reach, though still enormously challenging. Venus's ideas like floating cities are interesting and could outperform Mars in some respects. Closer gravity, better atmosphere for radiation shielding, more solar energy. But they are further from demonstrated feasibility. For long term, both have pros and cons. Mars might win because of being further from the sun. Easier to terraform perhaps, safer from eventual solar evolution.